Let me introduce myself. My name is Michael Rees. I'm a Principal Program Manager on the Azure Data Lake Big Data team at Microsoft. I'm here today to talk about how to take your R, Python, .NET code and scale it out with U-SQL inside the data lake to do custom processing on your data in a scaled out way. How many of you have used or heard about Data Lake and U-SQL? Okay, many. Anybody here who has never heard of it and just wants to learn? Okay, good, because that would be the wrong presentation. Will be a little bit hard for you to sometimes follow because I'm trying to stay at a pretty deep level. So feel free to come after me afterwards and ask me questions if you have any questions about it. So today what I will be doing is I will first talk a little bit about the characteristics of big data analytics programming and why we think that U-SQL is a really good framework to help you achieve your goal in doing big data analytics programming. I will then go and first give an example of how we are providing capabilities to you to scale out cognitive libraries that are basically the code that sits behind the cognitive services APIs that we got from those teams, and we make them available at no extra cost for you to use them inside your Azure Data Lake. Then I will use that as a motivation to go into the actual U-SQL extensibility framework, talk a little bit more about how that looks like, show one more example there with custom image processing that you can write yourself, basically. And then I will also talk about how we can take Python and R and scale it out. So let's get started. First, if you look at many of the big data processing needs that we have seen with many of our customers, both internal at Microsoft, in our own internal big data lake, as well as with external data lakes, and implementations, is that people often need to do very specific processing over the data. It's not all relational select from where group by aggregation. They often need to use specific algorithms to run on their data. Often the data is not even relational in nature. It's not a CSV file. It's often textual data or it's image data, etc. And at that point in time, you need to have the ability to take algorithms that are normally not easily expressed inside relational language and scale it out. Now, you have different approaches on doing so, but we think that giving you a declarative framework to put that in and then bring your own coding experience and scale it out is kind of the better way than giving you a programming experience where you have islands in which you talk to scaled out data, because you want to bring the processing to the data and not the other way around if you have a large amount of data. So if you look at existing languages such as SQL languages for big data processing, they give you the ability to do scale out and parallelization because they're declarative. You say select star from where, etc. So the system knows how to scale that out. You don't have to worry about that. But they are not really easily to extend. I'm not sure how many of you have tried to add a user-defined aggregator to Hive, but you have to implement 8 APIs, and you have to patch the server. I'm not sure how many companies allow you, each developer, to patch the server just to add some new code and disrupt the stability of the server. So it's not that easy. So on the other hand, if you look at programming languages for big data, and I take here the gamut from really low-level MapReduce libraries up to Spark with their kind of cascading link-like extensions to Python or Scala. Obviously, extensibility is very easy because you just write code and then you kind of call out into the frameworks that they have. But the declarativity is at best bolted on. So like obviously MapReduce, you don't have any declarativity. You have to make sure that you are setting up your scale-out infrastructure and manage that. That's one of the reasons why Hive got invented, was that people felt that was too complicated. Even in Spark, you have Spark SQL, but it's kind of, you have these islands within procedural code. So you don't have a global view of how to optimize, etc. So we think that U-SQL as a framework basically gives you both the declarativity and extensibility equally native, so you get the benefits of both without necessarily the drawbacks. In addition, it gives us the ability to take user code that I have written in .NET, in Python, in R, and then basically put it into the U-SQL framework, and that will give me the ability to scale that custom code out. Now, we'll go into more details exactly what that means with the examples that I'm going to show you so that you have a better understanding of some of the trade-offs that you have to do. Obviously, we are not going to just take any code and you just drop it in. You have to drop it in and then kind of use some simple APIs to call into the data. So here's a simple U-SQL example. On the left-hand side, what you see is a U-SQL script that does some processing. In this case, it does some extraction, schematizes some input files using a custom extractor. Then it does some selection on it, some transformation. That selection has the user-defined function in there. And then it does some output, and then it does some further processing, and does more outputs, etc. On the right-hand side, you see an operator graph, which is basically, or the job graph, which is basically kind of showing you how that declarative script got translated into my scaled-out execution graph. So if I look at this closely, you will notice that the extract statement, for example, is part of my declarative framework. Now, this is the language part that tells me go and scale out these user code items. Now, the operator graph is not necessarily one-to-one corresponding to the script because the optimizer and the job manager, etc., try to optimize that graph, so it sometimes puts several statements into a single vertex or into a single stage. But you kind of see that if you go through, you have these phases where you have a process, for example, and then you have the user code being executed by that process at scale. You have the output statements here, and then you have the user code for the output statements going out, etc. So that kind of shows you kind of the framework that you have. The language looks very much similar to SQL, but you have all these islands where you can put in your own user code and then have SQL or U-SQL scale it out for you over the data. Now, the languages, as I mentioned, are not just .NET, but it's also Python and R, and we are looking at some other languages as well. Now, U-SQL itself came out from us having an internal data lake, an internal data platform called Cosmos, and the language that we used in there is called Scope. So U-SQL is basically the next version of Scope. It kind of evolved out of that. We are using the C# and SQL integration model. Did a little bit of cleanup for external consumption because internal tools are always a little bit raggedy and designed for ad hoc for like that customer needs something yesterday, so we do it so that it works right away. So we cleaned that up, but we are still having the same optimization and scale-out model that we are having there. And the reason why I mention that is that we have hundreds of thousands of jobs daily running inside our own internal data lake. So basically, that framework has been proven over and over again over the last 10 years within Microsoft. We also took a look at some of the Hive capabilities, making sure that a Hive programmer feels comfortable with U-SQL. And of course, since we are in a data lake where we have multiple analytics engines, we're also working on doing data format alignments. We have text files like CSV support. You might have heard me speak yesterday where I announced that we are now starting to add Parquet support and in the next refresh. And then obviously we also looked at T-SQL and C-SQL for the framework part because we're not only scaling out your C# code, we also want to be able to scale out the standard SQL expressions. So for example, you might have windowing functions. Now, you can implement the windowing function in the context of what we call a reducer or a processor, but we probably, if you have an existing syntax that works, and people know that syntax, even though windowing functions is not the easiest syntax, making that available and allowing you to scale that out as well is obviously also part of our mission. So not just .NET, Python, and R, but even like SQL expressions we scale out as well. So let's switch over into some examples here. Let me switch over here. Now, one caveat here. If anybody in the back can't see this, please move forward. There are a lot of free spaces in the front of the room. I wouldn't like to hear people complaining about the font sizes. But if you have a problem seeing it, just let me know. So what you see here is this Visual Studio with the U-SQL Azure Data Lake extensions installed. And what you in particular see here is a script that does image processing. What I'm doing here is I'm referencing a couple of assemblies, image common and image tagging, which are assemblies that you can actually use on your own Azure Data Lake account. So let me show you quickly how you install that. If you're inside your portal here, let me find that quickly. You go from your Azure Data Lake portal view. There is up here sample scripts link. It's a little bit badly named. I'm asking them to have a separate button for this. And then over here, you have this more menu where you can install U-SQL extensions. Now you ask yourself, why isn't that already pre-installed? Well, it is installed inside your U-SQL database right now, and it's about 2.5 gigabytes of data. Now, storage is cheap, but we want you to opt in. If you're not using it, you probably shouldn't be paying for the storage space. Eventually, we might be moving it in completely so it's part of the system, but right now we are still kind of taking feedback and optimizing the experience, et cetera, and so we don't want to bake it in and then break everybody. That's easier to have people then opt into changes. So basically, that installs a couple of libraries. We'll go into more detail what the libraries are, but in this case, I'm using this image tagging. Now, what does this image tagging do? There's an extractor here that basically goes over images and identifies how many objects are in there, and it identifies what type of objects these are. And the result is returned in form of a SQL map here that has both the object that it finds and the confidence that the model provides that it really is of that object type. I mean, it might be that it says, well, it could be a microphone, but maybe it's an ice cream. So might not know exactly what it is. So what this script does is it basically now goes over a set of images that I have inside that folder. I have a local copy of that, so I can show you what the images look like. So some of you might have seen these images yesterday. I was kind of teasing this demo in my presentation yesterday. And you see here cars, animals, and some 1960s throwback pictures here as TIFF files. And if I look at my favorite picture to show, which is that little squirrel sitting on a rock, so we try to find now things that are in these images. So in this case, hopefully we'll see the animal in there and maybe some trees in the background, etc. So this is what this extraction does. Then the next thing I'm doing here is I'm saying, well, I have these virtual columns up here that I use to identify the name, wildcard the names and formats, and lift those file names and formats up into my row set. But I can also put a predicate on this row set. So I'm actually now operating on all the JPEG files that I might have inside my folder, but not the TIFF files. And then the next query just does a join here of my map into like a string representation, so I can output that information into my CSV file down here. Now, I did run that already, and I did run this query in two ways. I did run it with our current default file set behavior and with the new preview features for file set performance improvement. And I just figured I kind of in passing can show you that behavior. So this was the query execution that I did. You see it run about for 2 minutes. And you notice here, it's a little bit hard to read inside. Maybe let me zoom in. There are about 15-ish files, I think, that it operated on. If I zoom in, you will now see here all these files with the extraction that was processing. Now, this is a custom processor, and each of these files is between 1 to maybe 5 megabytes in size, so it's not that big, but I potentially have many of those. So the processing, the image tagging, is like running for about 5 to 6 seconds. If I look at the result, I can just double-click on the result down here. And open that up a bit. And you see kind of the result here. I think it was the 9617 was my squirrel. And you notice that with a high confidence here, it identified it as an animal. And it even identified it as a mammal here. As I mentioned yesterday, it doesn't know it's a squirrel because the model is not precise enough to identify it as a squirrel. But it has a lot of interesting, like it finds the boats, it finds the cars, it even knows that the car, one of the cars is at a race event and the other car isn't. So it's kind of like a pretty good model that we already have built in. Now, I did run the same job using the preview features, and in the preview features, the job was running for less than a minute, and the plan looks different. I only have 1 vertex here, so instead of using 15 vertices that are costing me potentially, when I scale those out, quite a bit more, in this case, I actually could run this with 2 vertices at most in parallel, and because these images were all packed together, and so it's more efficient. So this is just kind of a preview of these performance improvements that you can get by enabling them currently as a preview feature. Okay, so now let's go back to my presentation and continue here. By the way, most of these code samples that I have are available on our GitHub site, and I also have links to the documentation that talk more about these different items in detail. So in terms of the libraries that we have available in the cognitive services context is we have face SDK, image and motion detection, image tagging, and OCR capabilities. These are all code pieces that are running behind the cognitive services APIs. These teams were nice enough to give us the code so that we can wrap it up into our extensibility framework and share it with you so that you can do some interesting stuff with the data out of the box. On the text analysis side, we have text sentiment analysis and text key phrase analysis. Again, it's done either using extractors, producers, or what we call appliers. So here's a more complex example. I have a set of images inside a table. And I basically, in my first statement, the object statement there, what I do is I get my image tagged, like what you've seen earlier. Then I get more information out. I look for the tags that contain dogs and cats. And then in the next step, I'm taking, again, my faces, and I apply the emotion analysis. In this case, I get a lot of information back about where the faces are, which bounding boxes they are in, what is the emotion that it's showing, again, what is the confidence for that. And then I correlate them together to find out basically what emotions, if the dogs and cats are happy or not, basically. Important if you are a pet owner, I guess. So the whole offering that we have there is just using our own U-SQL extensibility framework to scale out your code. So there are different ways of adding custom processing to U-SQL. The easiest one is that U-SQL's scalar expression language, like what you put into a where predicate, is C#. So you can call any C# user-defined expression or user-defined function in that. In addition, we give you the ability to define user-defined aggregators in your language and user-defined operators. And this talk will be primarily focusing on the last one, on user-defined operators, because that's where you really get a lot of power to process row sets at scale. So what are UDOs? These are basically custom operators in the language of your choice. You can do user-defined extractors, converts files into row sets. You have user-defined outputters, convert row sets into files. And there are some more examples in my presentation yesterday, so I'm not going to go show a lot of those here. We do have user-defined processors. User-defined processors take one row in and one row out and have the ability to be generic and understand the schema. So you could think of this basically just as a select statement with a lot of UDFs inside your select class. The benefit of and that's often better for optimizer processing. But if you have a lot of memory-intensive processing where the UDF need to create a lot of memories and you have a lot of values that you have to pass in, then that becomes not as efficient because you generate a lot of memory pressure. By using a processor, you potentially only have to use memory once, and then you can use it for basically the whole for every single column that you're returning for the row. The other thing is you can make decisions based on the data types of your expected output schema or input schema, and you can make decisions based on the names of your columns that come in and out, which again is something that is a little bit more powerful than just using a user-defined function. We have user-defined appliers, which are taking one row and produce 0 to n rows. It's invoked with an outer or cross apply, so it's like a table-valued function in a sense. We have user-defined combiners that are like a user-defined join. So that takes two row sets in and allows you to combine them with some custom algorithm that you might have designed to kind of join them. So think of potentially applying a model to a row set, and the model itself is represented in a row set as well. And then the most generic of them, it's called a reducer, because it's like in MapReduce, it's in the reduce phase. However, it takes n rows and gives you back m rows. Now, reduce would mean that m is less than n, so you return less rows than you pass in. But as you will see, you don't have to do less. It's just that the optimizer assumes so. So if you return more, you might have to give an optimizer hint to make sure that the optimizer understands what's coming back. Now, all these user-defined operators, as I mentioned earlier, are scaled out by these specific U-SQL expressions. So it's basically kind of a combination of these two concepts. So now let me show you another example where I'm actually, instead of using something pre-canned, I went and took some existing .NET library functions and wrapped them into some user-defined extractor to do image extraction. In this case, I have my same set of images that I have, and I created my own assembly called images. And what I do in that assembly is I'm basically having an image feature extractor. Now, this image feature extractor has a few interesting properties. The first thing is, depending on what column I provide here, it will decide to give me back the EXIF properties. These are these meta properties that are inside JPEG files that tell me, for example, what the camera was, what the camera model was. In this case, I'm also looking for the description of the image and the copyright notice that might be on the image. In addition, I can create a thumbnail out of the image and do some other stuff. And then what I do here is again, I put my filter on so that I'm only operating on the files that are actually JPEGs, because TIFF would give me an error. And then I output it. And then the second step here, I run on these images. I take the thumbnail and I use my image outputter, which is a custom outputter that just basically takes a blob and writes the blob unchanged into a file without putting any quotes around or anything. And basically write out my thumbnail here. Now, I did run that job locally this time, so let me see if I can open up that window here. So, and again, you notice here that the job graph shows me that I was running a lot of on these files. Now, the view here is a little bit different because I actually did run this locally on my laptop. I'm not running it because my laptop is a little bit slow today. But you can then see on the output list here, on the local run results, let me zoom in here. Down here, you basically see on the one hand the image features that I extracted, and on the other hand the thumbnail. So let's do first the image features here. Oops, it says I can't preview the string. So let me quickly, that's nice, or not. Okay, let me just go to the actual browser here. I can do that here as well. Go into my local run folder, output, and then date modified. It's restarting. Anyway, so what it basically gives me, it gives me the result that I was looking for with respect to the images. Here is my image folder. So you see here is the thumbnail, so the picture got reduced. And here is my CSV file, which I conveniently linked up with Excel, so I can just open Excel to take a look at it. Obviously, oops, come on. And so you see here, a lot of data here is just the thumbnail, but you see here that like many of these pictures were taken with a Sony DSC RX100 camera. Further below, if I reformat that a bit, there is also, like here is, for example, a description, staycation, for example, taken by a Canon camera, etc. So all that information is now extracted. Now let's take a look at the actual code that was generating this. I assume that I got recovered, so let's go back here and just take a look at this extractor. Increasing font size. So this was the code that I've written. I was making use of my System.io drawing libraries, which are built in. And I'm now basically writing a specific image feature extractor down here on line 25. Now, since images are not splittable, I have to see the whole image to be able to like extract information out of it. I defined this extractor so that I have to be able to see the whole image and the processing doesn't split it. If I have a CSV file, for example, then actually we split the CSV files into chunks if it's like bigger than 1 gigabyte, and we actually parallelize that out. This setting just makes sure that I'm not accidentally splitting my file and suddenly get runtime errors. So in this class here, I basically implement two things. I do my class initializer over down here, which basically just gives me the parameters for my extractor in this case. And then I override the iExtract method. That's here. So what I get here in the iExtractor is I get my input, and then I return a collection of rows, IEnumerable of rows here. Now, in this process, what I do here is I create an image byte array on that input stream. So that basically loads the image into memory. But it only loads it once into memory. And then what I'm looking for here is, depending on if a column got requested, I will be executing a lambda expression. Now, why do I do that? Why don't I like just execute it anyway? I want to make sure that I'm only executing these operations if they're actually requested. So what I'm doing here is I basically make sure that I'm not doing too much processing. So I have flexibility in requesting columns. And if I don't request a certain column, I'm not going to do the processing. And that's it. That's my user code here. So So I only write this extractor API interface, and then within that, I can call out into all my specific user code that I have inherited from either myself or some colleague or from some online repository, etc. So let's go back to the presentation and maybe make a quick stop and ask if there are any questions so far. If not, then let's continue. So as you have seen now, we basically wrote our own code, not just something that we provide out of the box, to do some interesting image processing. Now, how do we specify these .NET UDOs? We have a .NET API that we provide to build UDOs. You can use any .NET language, not just C#, although C# is kind of the one that we support easily out of the box. But I've known people that wrote UDOs using F#, for example. I haven't seen anyone using VB.NET yet, but maybe you are the first one. Once you have written that and compiled it, you basically then upload the DLL to Azure Data Lake Store and register it with a U-SQL script. Now, the Visual Studio actually gives you tool support, so let me quickly show you that. When you are looking over here, you see this C# project for U-SQL project. If I right-click on this, it has to be in a U-SQL project, but if I right-click on this, there is a Register Assembly menu. And that gives me the ability to go and basically say which database I want to load the assembly in, what is the name that I want to give you. If I want to override it, I can add additional dependencies and additional files. And I can even include debug information so that if I do my clusters level debug and I want to be able to download a failed vertex, then that gives me all the PDB and source code files already, so I don't have to hunt around and try to search them on some developer box. So that kind of gives me a very easy way of doing debugging if the code fails even in the cluster itself. So that's kind of how you register the assemblies. And then basically you can do what I was talking about, basically call all these managed codes. There are a few limitations to UDOs. We scale out your UDO code in a shared nothing environment. Like each one of these containers cannot talk to their other containers. And you don't want that to happen, because once that would start to happen, it would have non-deterministic behaviors. And you couldn't optimize it anymore. So what you want to do is basically you want to have them completely independent, scaled out, running over the data. One of the other things that we are disallowing is you cannot reach out to web services. Like we have quite a few customers who come and say, I would like to call this web service, or I want to call into this other product, like let's say Azure Functions or so, from within the UDO. The reason why we do not allow that is that if you have 100 million rows, you scale that out over 100 nodes, each node operating on 1 million row, each row getting called into a web service API. You will have the perfect distributed denial of service attack. So as a result, that service most likely will go down because we will completely overload it. Secondly, after that, somebody will be very mad at Microsoft because they will know which IP address that was and will blacklist Azure as an acceptable IP address. Neither of which we want to have happen, so therefore we disallow this. If you need to go and access data through a web service API, you will have to find another way of getting at the data and load it into the data lake, or come and plead with us that we find some way of making it a built-in experience. Like one built-in experience that we have right now is you can reach out to SQL Server instances. And the reason why we allow you to do that is because we take control over how we communicate with those instances to make sure that we are not getting into this situation of a distributed denial of service attack. So there are different ways also how to specify the UDOs. You can do code behind. So what code behind means is that within the Visual Studio experience, you have an additional script file here that is either C#, .NET, or Python. We'll see the Python one in a minute. And then you just, inside that, you put your code in. And then U-SQL, the Visual Studio experience, actually will then compile this and upload it, register it, and at the end remove it again, so to make sure that it's not like an artifact that hangs around. This is very useful if you just want to share some scripts and some code and really don't want to persist the assembly inside the metadata store. However, if you want to share it, you can create your class projects, and then what you've seen earlier, then also register that inside the database, and then you can reuse it over many script invocations. Obviously, only will have to register one. I've seen sometimes customers do to create the assembly every time they run the script. That is really not needed. You create it once, and then you reference it multiple times. The UDO model, you saw it earlier. I showed you the extraction for images. That gives you an abstraction level directly at the byte stream level. We have a second level of abstraction when you want to basically read rows. And so this is kind of shown here. So again, you mark your UDO. It's an I extractor, I processor, so it's an implementation of a class interface. And then you mark it up with that attribute tag as well. You can parameterize it with doing the constructor and provide the parameters then as private internal class variables. And then you override the UDO, depending on which UDO you're implementing, and then you have the UDO-specific processing pattern. Here now, let me zoom in again, you see the processing pattern that is specific if you do row-oriented processing. Now, row-oriented processing is kind of interesting because we implement it in a way that we allow you to split your data, assuming each input row is less than 4 megabytes. And then you can have, let's say, a 100-gigabyte file will be split into 100 nodes, and each one can be executed on in parallel. Now, obviously, your rows will not align with that size. So we will have to peek into the next one for 4 megabytes to make sure that you get the right data and see that. And that's all abstracted here underneath that, underneath the interface here, input.split. That kind of is abstracting from that. So your programming model is much easier. You don't have to worry about that overflow, etc. So we also have access to the row set, and there's schemas in the UDOs. And you can either set the output by position or by name. So you have a lot of abilities to do interesting things with understanding the data types and the schema names that you are getting on the input and on the output. We talked about managing assemblies. You referenced them. In terms of built-in assemblies, there's a certain set of built-in assemblies that we deploy. The U-SQL specific ones, we have a few system-specific ones that I list here. We do not deploy all the system assemblies because deploying assemblies costs time. And so we kind of give you the core, and then if you need anything else, you tell us. So in this case, if you need system.xml, which is one of the assemblies that we don't deploy automatically, you just say reference system assembly and give us a quoted identifier of the name of the assembly. You can enumerate assemblies with PowerShell commands, U-SQL Server Studio, PowerShell, even catalog views nowadays. And you can drop the assemblies using drop assembly. Now, how many of you know SQL Server's assembly? Nobody? Good, then I don't have to talk about one person. So unlike assemblies in SQL Server that have to be signed and you have to enable it and you have to put in wrapper functions for each function that you're exposing. Here it doesn't matter, anything that is public inside the assembly is usable once you have it loaded. That's one of the benefits of running in a container so that you can't really destroy the system, so to speak, which was one of the worries that the SQL Server guys had. And also, because we have C# as the expression language, it's very easy to just call into those expressions. And we talked about Visual Studio making it easy. Now, sometimes you need additional libraries or additional configuration files, etc. You can, and you don't want to register them together with the assembly because they might be changing between different invocations of the script. So we give you an ability to deploy resources, files that live inside Azure Data Lake Store onto a vertex so that you can use them on the local path from within your user-defined operator. We will be making a lot of use of that once we start looking at Python and R, so that's why I'm mentioning that here. So that's basically moved in there. There are some limits there. A single resource file can be at most 4 megabytes, and all the resources that will be deployed, code and resource files, is 3 gigabytes per node at this point in time. So how does that look like then? Well, if I take my U-SQL script, I compile and optimize it. I look at my metadata system to get my reference assembly, so I get all the assemblies that I have referenced in my script. And I look at the deployed resources in my script as well, and I get those from the store. They will basically be put into what we call a job folder. Now, each vertex will basically get the C++ and C# code that we generate from your U-SQL script. In addition, any additional assembly that we reference will be put in there. And this could be a managed DLL, or it could be a native DLL. Like if you register SQL Server spatial libraries, for example, you would have a managed and a native DLL that you can deploy. And then any additional files will also be deployed that you have through deploy resources. So once you have that, then basically that gets deployed to the vertex. And deploying to the vertex of this, of course, will cost you time. So therefore, we kind of recommend that you only really reference the assemblies that you need. As an example, I had one customer who had taken our cognitive services libraries and was complaining that it was slow. And I looked at it, and he included all of them, but only used one. So by just like not including all of them, it was suddenly like 2 times faster. So now let's take a look at Python. How many of you yesterday saw me do tweet analysis? So let's do tweet analysis with Python instead. Let me go over here. Of course, my password has been so in this case now, I again have my tweet extract here. Now, with that U-SQL extension installation, you also get a library that allows you to invoke Python programs. In this case here, what I do is, let's skip over the Python program itself. I again go to my tweet sample data, which contains basically authors and tweets, etc. And what I do here is I basically now, on this input row set, I do some transformations using some Python program. That's done with this statement here. Now, the Python program that I'm invoking is basically extracting both my mentions and my topics. So basically my @ names and my hash names, hashtags out of my tweets. And as you can see, the tweet, I have here 2 tweet functions that just are some string manipulations in Python. And then down here is my main program. And that's kind of the contract that I have to fulfill. Now, the contract in this case is that I take a data frame in and I output a data frame out, and I'm just doing Python on the data frame. Now, I know a lot of Python programmers right now write their code directly against files. So in order to be able to run Python code in U-SQL, you will have to make sure that you're operating from a data frame to another data frame. But otherwise, the logic is exactly the same that you can do in there. So in this case, I basically get my mentions and my topics out. And then I do some cleanup here. If there's no mention and no topics, I just kind of leave them out, and I run this and return this. So let me see which job I did run this on. So this is the job that I run this on, and you notice here that I had 10 input files. And I was operating here on the stages. Now in the portal, actually, if I go over to the portal quickly, the job graph actually tells me that I'm running a Python program inside my Vertex. This is a feature that we are also going to add to Visual Studio, but right now you can only see it in the portal, so I switched over quickly. So let's go back here. And if I look at the result, let me see if I can open a previously opened file here. You now see that I basically have my authors here with my mentions. Again, we would have to do some additional cleanup because some of these @ have more punctuation afterwards. And over here you see the topics. And you notice that many of these people talk about Power BI and Azure and big data, etc. So I did run now a Python program against my data. Now, I can do other things with Python. I can take, for example, a look at, let's close this. I can, for example, look at import a custom module. Now, in this case, the custom module, you package it up as a zip file, and you deploy the resource here additionally, instead of just doing the reference assembly. Now, in this module here, I just have a simple mymodule.hello-world program, so it's not a very interesting zip, but this is kind of what you do. So basically, this file gets deployed into the local disk on the Vertex, and so I can just get it from my system path, in this case, and import the module, and then use that inside my main function. Now, in this example library, I did run this on a 0 input set because this library wasn't doing any processing based on any incoming data, so I kind of faked the dummy row, and then I'm kind of applying that to this single row to create that hello world string. So very simple to do. I can do versions of Python, figure out what it is. So in this case, again, I just have my U-SQL script, use my sys library to tell me what version of Python it is, etc. All very simple, only very Python-esque, as they say. Now, I mentioned earlier that I can do code behind on C#, and I can also do code behind on on Python. So if I right-click my U-SQL file over here, I can right-click and I can say add UDO. And now this add UDO here gives me the ability to add a Python, R, or C# UDO. It's actually not just UDO, it's just code behind in general. So I did that down here. So in this case, there is no Python code inside my U-SQL script. The only thing I do here is I refer to the name of my code behind file. And then the code behind file here contains the actual Python script, same one that I had before. Now, when you look at the actual execution, Visual Studio does a lot of interesting stuff to it. So it actually will go and take the code behind file and inline it in my automated generated header code, and then will pass this as the script in here. So it actually goes and changes the script for you to make it an easier experience, so you can have your Python file separately from your code file, which makes it sometimes easier to like debug and maintain it. Okay, so this is Python. Let's go and summarize some of these items here. You can use U-SQL to scale out your Python program. The Python code can contain references to libraries such as NumPy, Pandas, the data frames that we're using, Skylit, and a few other libraries. And any library that you want to add, you can normally do with the with the zip file extensions. There are two caveats. One is that you can only use up to about ½ gigabyte of memory inside your Python program per node. We are working on giving you an ability to increase that limit if you need to, but right now that's the limit that you have. The other thing is that these files are being placed inside your local directory inside your node, and that's running on Windows, so there's a file path length limitation in Windows that I've noticed some libraries might exceed if you extract them. So there are some like tricks about using like volume mounts, etc., to kind of get around that limitation. So we already talked about this. I'm skipping over that. Now the vertex execution path vertex code generation looks very similar. So I compile my U-SQL, I reference my extension Python library, which is a .NET library that we provide, and then you can deploy your resources for scripts, for other libraries, etc. as well. And then instead of just running C# and the C++ runtime, we are also running a Python runtime inside the vertex. And we do the kind of marshalling. So let me show you that. So if I have a reduce stage, for example, where I invoke my Python program, I will have my row sets partitioned based on my reducer partitioning. And then each reduce vertex will basically have this Python or R reducer. The same holds for the R implementation as well, which does the type mapping and the marshalling of my row set into the data frame. And then the data frame gets processed by your Python and R code and returns another data frame, and then that just gets like processed back out into the next stage as a row set. So a very simple processing model. Now, of course, you notice that there is like a few layers through which the data goes. So you go through your like reducer and then go into Python. One thing that we are currently working on for future release is the ability to actually write what we call native Python UDOs, specifically extractors and reducers, that give you the ability to just register the Python code directly as an assembly, as a U-SQL assembly, and then you don't even have to like wrap it into a UDO code invocation. Then you can just basically use Python directly. And we will be using a similar API, like either a stream API, byte stream API for extractions, and data frame APIs for row sets, so that you can build your own UDO. So we're removing one level of indirection in an upcoming version. So now I mentioned R, so we can do the same thing with R. Let me go over and show you that. In this case, again, we have an assembly that you get with that extension. And what I do here is I show you the code for both doing model generation in U-SQL and then applying the model to do scoring, or prediction in this case. So what I do here is I have an iris data set, a CSV file, and I output my model to some location inside my data lake. Now here's the R script that I want to run. And again, we could do that with code behind, or we could do that through a file that we put into the data lake. There are different ways of doing that. Again, it goes from data frame to data frame. So input from U-SQL is the data frame that we're getting. We're expecting that there's a species column, and we are then basically doing an AS factor on it. And then you're basically seeing here the whole model that we are kind of doing classifications of species based on the information that we get from our input data set. And then we basically create our model out of this. I'm not an R expert, I have to admit. But I've been told that this is what it's doing what I'm telling you. I did run it, though, and it works. Then what you do is basically you use your input data set in U-SQL, using an extractor, for example, of your data, as your model training set. And then, like before, you use a reducer here to operate on this data frame to return the data. Now, one important aspect here is and that's kind of important in terms of scale out. If your model needs to see all the data, again, you have to be careful about memory limitations. Like, you cannot have more than half a gig of memory allocated right now. The other thing is, so a reduce all means that all the data goes into a single vertex. So that single vertex might become somewhat of a bottleneck. It doesn't get scaled out. Why is it still useful to do U-SQL for model generation? Well, sometimes your model generation might be partitionable. Maybe you can create submodels for different partitions and then combine those models into a single model. At that point in time, that might be useful. Another thing is, sometimes you create a bunch of different models with different coefficients and parameters. And then you want to apply those models against your test data to figure out which one of those models is better suited, which one of these parameters was better for my model. So at that point in time, you can parallelize your model creation, and then you can parallelize the testing of the model against your test data set to determine which one is better. And then you can take the better one and scale that one out to process against your actual data that you want to predict on. So in this case, I have my iris prediction here. Again, in this case, I deploy my model that I created earlier. And again, I run my R script here. This time it's much smaller. I just load my deployed resource, and then I basically do my prediction using R. And that gives me a prediction for the input data set. Now, in this case, what I do is I can parallelize this prediction. Sometimes the prediction can be parallelized based on some intrinsic data characteristics. Let's say I predicted based on a region or so. Sometimes you have to create a random number or some partition number that allows you to partition the data artificially so that you get scale out, which is what we're doing here. So just to show you that the job actually run, here is the iris prediction. Here is the iris prediction.csv here, and you kind of see the partition number here that we operated on, 0 and 1. And then you see the fit, the LWR and UpR values that are coming out from the model to allow you to basically score the probability of what type of iris or flower, type of iris flower this, the input data is. So let's go and summarize the R part. As I mentioned, you can generate models, and you can use a previously generated model both. The code is, again, fairly simple. Again, the main aspect is you take a data frame in and you output a data frame. That's kind of the thing that you have to think about. The Vertex code is exactly similar to what we had earlier with Python, except for that instead of having Python, you have R as a runtime. Right now, we are using, I think, an open source R runtime that we marshal through r.net. We are looking, again, at sometimes in the future to potentially have a deeper integration into the R stack. And at some point, we might even be thinking of doing R server that allows you to scale out within R. Now, that's a little bit harder because you have a scale-out engine within a scale-out engine. So you don't want to suddenly have, let's say, the outer scale-out be to 100 nodes, and then the inner scale-out be to another 100 nodes, and suddenly you have 10,000 nodes that you pay for. So we have to figure out how to do that in a meaningful way. So now to summarize. I hope that you have seen now how you can bring your own code, either existing code or your own custom code in .NET, Python, R, and scale it out with U-SQL at a very large scale in your data lake. I have ... here because I didn't want to put that onto a slide. Obviously, there is one language missing, or one language family missing, that starts with J. We are working on providing the ability to write UDOs in the JVM-based languages as well. Hopefully, we'll have a preview by early next year for that. And that would be similar to what we do also with .NET then. So to kind of summarize here, there are other presentations that are related to Azure Data Lake and big data processing. You have them here. They all have passed, I think, so I hope you have had time to attend them. Otherwise, please catch them on the recording once they become available. We still have hands-on labs available where you can also play with the cognitive libraries. Here are some lists of links, etc., that you can go and find some more information. This is obviously on the slide deck, so don't feel free to grab that once that becomes available. Now, any questions? Can you please stand up and maybe stand in line for the... Sure. Yes.
So I just want to clarify on the R part, right? So you're using probably just a Crayon R open source package, not the Microsoft R, it sounds like, right? This
right now, yes, because of the, our server is not deployable into
right.
Vertex.
So I just want to make sure I understand that right. So I mean, what the benefit of our server is it does the scaling for you because those particular functions know how to do that.
Yeah.
In this case, we would have to essentially keep in mind that if we're scaling out and then we're essentially hand coding the scale out ourselves, leveraging this as the engine to do the scale out.
Well, you're not hand coding in that sense. You're using the U-SQL declarative framework to do the scale out.
Right, to actually do the scale out, but as we program that, we have to keep in mind that it's going to do the scale out versus when you use our server, you just kind of write your program and then you throw it over there and it figures out how to do that.
Correct, but our server scale out is potentially different and doesn't scale to that amount of data.
Right, no, I get it. Okay, and just one last thing, because I know people are going to ask, if we can find out specifically exactly what are libraries and things like that?
Yes, it's all in the documentation.
If we document that somewhere, okay. Yes. Because I know it's going to be a question.
Yes. And again, you can bring in your own libraries, like we did with Python, and then basically install them as part of the script process as well. Yes.
So if you create a custom extractor UDO, can Visual Studio debug or step into that to help you figure that out?
Yes, so Visual Studio cannot step into the U-SQL code because that's a declarative thing that gets rearranged and you don't really know where the breakpoint is. But any UDO that you have in .NET that Visual Studio understands how to set breakpoints on, you can set breakpoints on. You can do it either with in your local run environment, so you can test it before you deploy it into the cloud. You can deploy it on your local run environment and debug it there. Or if you have a failure, for example, a runtime failure on one of the vertices, you can download the vertex. It will download the input data and all the code that was running on that vertex, and then you can set breakpoints and do a local debug of that cluster node and see what led to the runtime error.
Okay, and kind of a follow-up question: if you register that custom assembly with your local environment, and then you make changes, do you have to re-register it, or is it smart enough to?
You do have to re-register it. The reason why we make you re-register it is we want to make sure that you know which version you're operating on, and that it doesn't automatically change behind you depending on what's happening. Now, it's an additional step that you have to do that the tooling fortunately makes somewhat easy, but that's kind of a trade-off between suddenly having things change on you without you expecting it versus having some control over it to make sure that you have the right version.
Okay, thank you.
Welcome. Any more questions? If not, please evaluate the session. Of course, I only take anything 5 and above, as I mentioned yesterday as well. If you have anything below that, I'm very looking forward to hearing your comments about how to improve the session. I also would like you to enjoy the party tonight. Let's hope we don't have any thunderstorms that shut down all the rides. Enjoy your lunch. Thank you.